So we're going to use the information we know about decomposition reactions, that the compound is going to decompose into the elements that make up that compound. So for water, we've got hydrogen and oxygen are the two elements that make up the compound. And so as elements, hydrogen is found in pairs as a gas, and oxygen is also found in pairs as a gas. And so those are my two products when water decomposes. Now I want to balance, and so as I go through my balancing, I can see that hydrogen is balanced, but when I look at oxygen, oxygen has 2, but my water, there's only 1 there. So that means I'm going to need a coefficient of 2 in front of water. And now I've got 2 oxygen, 2 oxygen. So my oxygens are balanced. But if I look at my hydrogens, I've got 2 water molecules, which will give me 4 hydrogens. So 2 times 2 gives me 4. And I only have 2 hydrogens in that formula for the hydrogen as the element. So I'm going to need a coefficient of 2 in front of the hydrogen so that I've got hydrogen balance as well. Let's take a look at our next example. Here I've got Al2, or aluminium oxide. So I've got 2 aluminiums and I've got 3 oxygens. So the elements that make up aluminium oxide is aluminum, and he's a solid as an element at room temperature, and oxygen. Now when it comes to balancing this guy, this is where it can get a little tricky. I can balance aluminum first, and I've got 2 aluminums in my reactant, so that gives me a coefficient of 2 in front of the aluminium. But when I look at oxygen, I've got 3 in the aluminum oxide, but I have 2 here, and that comes in one oxygen molecule. And so I can't split an oxygen molecule, so I need to find that common multiple between oxygen, or between 2 and 3. And in this case, the lowest common multiple between 2 and 3 is 6. And so what I can multiply 2 by to get 6 is a coefficient of 3. So now I've got 6 oxygens on my reactants, or my product side, and I'm going to need a coefficient of 2 in front of the aluminum oxide so I can have 6 oxygens on my reactant side. But as soon as I do that, I no longer have my aluminum being balanced. So I need to go back and rebalance aluminum. So with aluminum, I've got 2 aluminum oxides. Each aluminum oxide has 2 aluminums. So 2 times 2 gives me 4. So that means I'm going to need a coefficient of 4 in front of the aluminum element. Because we have to go back and forth, it's always recommended to do those elements that come by themselves last, because it's easy to fix those guys up afterwards. So let's do the next example here. Here I've got an iron oxide, and it looks like it is iron 3 oxide. And so I've got both iron and oxygen here. So my products are going to be iron, and my other product, it'll be also oxygen gas. And I'm going to balance oxygen first this time. And as we can see, oxygen in our reactant, I've got 3 of them. I only have 2 in my oxygen as a molecule. So that lowest common multiple again is going to be 6. So that means I'm going to need a coefficient of 3 in front of my oxygen element. And so that's 3 times 2 gives me my 6. That also means I'm going to need a 2 in front of my iron oxide so that I also get 6 oxygens. Now, when it comes to iron, I'm ready to balance that iron, or the Fe, and I've got 2 iron oxides, and every iron oxide gives me 2 irons. So that's going to be 2 times 2, which means I've got 4 of my iron oxides. Now let's take a look at solid aluminium oxide. So initially, it's like, okay, what do I have here? Well, I strongly recommend finishing this guy off. So I've got solid aluminium oxide, that's a word, breaking him up into his product, that would be aluminium. That's the element that makes up the cation, plus oxygen, that's the element that made the anion. Now, if I want to balance this guy, I need to write out what his formula is. So aluminum makes the 3 positive cation, oxygen makes the 2 negative. If we do a crisscross, that means I'm going to need 2 aluminum and 3 of the oxygen. And oh, wait a minute. This happens to be the same guy that we just did up here. So I'm not going to balance him again, but I am just going to write it out, and I'll leave that for you guys to balance. So this last guy, he's not balanced. So it's just a skeleton that I've left here. Let's take a look at our solid nickel 2 chloride. So I've got nickel is what's forming my cation, so that's my nickel, plus chloride. The chlorine is what makes the chloride ion. So if I'm going to write this as my skeleton and then balance, then I'm just going to take my nickel. That 2 tells me it's the nickel 2 positive ion. Looking up on my periodic table, chlorine makes the negative ion. Doing a crisscross, I need 1 of the nickel ion, and I'm going to need 2 for the chloride ion to get a neutral compound. So it would be Ni nickel, 2 of the chloride ion. He's solid, and he decomposes into nickel, which comes by himself as a metal, plus chlorine. And again, chlorine is one of those diatomic elements that comes in pairs. Now I want to check to balance. When it comes to my chlorine, I've got 2 in my reactant, got 2 in my product, chlorine's balanced. When I look at my nickel, I've got 1 in my reactant and I've got 1 in my product, so he is balanced and I don't need to worry about that one. This last guy, he's going to be a tricky one to balance, and this is because we've got a bunch of different elements. So this is an example where I've got a complicated compound that is decomposing into 2 smaller or more simple compounds. So we've got H2CO3 is decomposing into water and carbon dioxide. So when it comes to balancing this guy, let's take a look at where we're at. So I've got, on this case, I've got 2 hydrogens on my reactant side. Bringing that guy down, I've got 2 hydrogens. So hydrogen is balanced. I've got 1 carbon. On my reactant side, I've got 1 carbon. On my reactant side, I've got 3 oxygens. And for oxygen, I've got 1 oxygen at water. And I've got 2 oxygens for, I'm just going to put a dash between these guys because it looks like 10 and 20. 2 oxygens. And so when I add that up, I've got a total of 3 oxygens on my reactant side. So it looks like it's already balanced as it's written. And it's just an example of where I've got a complicated compound decomposing into 2 more simple compounds, where I'm going from having 3 elements in my compound to only having 2 elements in my compound. And that's another example of a decomposition reaction. though you will only have to predict the products for a decomposition reactant when it's decomposing into its elements.